Let's do another one of these same problems of calculating the pH of a salt solution. So this ALEKS problem is giving us a 0.94 molar solution of ammonium bromide, and it is telling us that ammonia is a weak base and giving us the pKb for that particular weak base. So our first job with a problem like this is to start by writing out the dissociation of the ionic compound NH4Br, and we're going to separate that into its cations and its anions. And the hint that you have here, the thing that you should recognize, is bromide. That's a very common ion. So knowing that that's a very common ion, that means the other piece of this ionic compound is NH4+. And we're going to make an ice table for this dissociation. The problem tells us that we have 0.94 molar NH4Br, and that is totally dissociating. This is a forward reaction. So minus 0.94 plus 0.94 plus 0.94, and when this dissociation is over, here's what we end up with for our cation and anion. Second thing that we have to do is figure out from the products of this dissociation, the NH4 plus and the Br minus, what are they? Are they acidic? Are they basic? Are they neutral? So this is where you would need to go back to your notes, 16.10, and look at cations first. Cations can either be neutral or acidic. You have a list of neutral cations, and NH4 plus is not one of them. So that means that this cation is acidic. Now look at your anions. You have a list of neutral anions, and bromide is one of the neutral anions. We've determined that NH4 plus is the acidic component. So that means that the NH4 plus ion is what dictates the pH of this solution, and therefore it is what we will use when we write our next equation. We're trying to figure out how acidic is this NH4 plus solution. Always, 100% of the time, with all of these reactions, it is our acid, or the base, plus H2O in equilibrium every single time. When we know that our reactant is acidic, one of the products of this reaction is H3O plus every single time. For the other product of this reaction, we have to ask ourselves, where did that H3O plus come from? How did it get made? We moved a hydrogen from the acid over to the water molecule, which left NH4 plus as just NH3. Make an ice table for this reaction using the end of the previous ice table as much as we can. 0.94 for the NH4 plus, no products yet. We don't know how much of this is going to dissociate or how much of it's going to react, so we're going to use X. 0.94 minus X, but we do know that X is very small, so we're going to approximate 0.94 is our ending concentration of NH4 plus. Now we're going to write an equilibrium expression. We know that this is an acid because it's an acidic cation, so that means that we are writing a Ka. Ka is our products, X squared, over our reactant, 0.94. And now we need to solve for X. The problem gave us the pKb, which we cannot use directly in this equilibrium expression. The pKb is 4.75. We can use that to figure out the pKa. pKa plus pKb is 14. So our pKa is 9.25. And we can take the antilog of the pKa, 10 to the negative pKa, and that will give us the Ka, 10 to the negative 9.25. So we're going to go back up to our equilibrium expression. Ka, 10 to the negative 9.25, is equal to x squared over 0.94. We are going to solve for x, 10 to the negative 9.25 times 0.94. Take the square root of that. X is 2.30 times 10 to the minus 5. X is the H3O plus concentration. So we are able to plug that straight into the pH equation. And our pH for this is going to be 4.64.